Query processing external sort-merge algorithm. By the end of this session, you'll be able to use the external sort-merge algorithm to sort large data, and you'll also be able to calculate and explain how much time and work it takes. Sorting operation. Sorting is needed when SQL queries ask for the result to be in a specific order. It is also used to make query processing faster and more efficient. Sorting operation. In logical sorting, we sort a relation by creating an index on the sort key. Then we use that index to read the tuples in sorted order. But reading tuples like this can cause a disk access for each record. That becomes very costly because the number of records can be much larger than the number of blocks. So, instead of only sorting logically, it can be better to store the records in physical sorted order. If a relation fits completely in main memory, we can use normal sorting methods like quicksort or merge sort. But if the relation is larger than main memory, we use the external sort-merge algorithm. Sorting relations that don't fit in memory is called external sorting. External sort-merge algorithm. Let M represent the number of blocks available in main memory for sorting. In the first stage of the external sort-merge algorithm, we create several sorted runs. Each run is sorted, but it contains only a portion of the records, not the entire relation. We start with I equal to 0. Then we repeatedly read M blocks of the relation, or whatever data is left if it's smaller. We sort this data while it is in memory. After sorting, we write the result into a run file called re. Then we increase I by 1. We repeat this process until we reach the end of the relation. Now continue with second stage. In the second stage, all the sorted runs are merged together. The total number of runs, called n, is less than m. This allows us to use one memory block for each run and still keep one block for the output. First, we read one block from each run file into memory. Then we repeatedly compare the first tuple from all buffer blocks and pick the smallest one. That tuple is written to the output and removed from the buffer. If any run's buffer becomes empty and it is not the end of that run, we read the next block from that run into memory. We keep repeating these steps until all the input buffer blocks are empty. After the merge stage, the output we get is a fully sorted relation. The output file is buffered, so we can reduce how many disk write operations happen. And since we merge n runs at the same time, this is called an n-way merge.
So, consider the example that we are having file size of a file of size 5 gigabits. Or, relation of 5 gigabits and memory size available is only 1 gigabit. It means that this complete 5 gigabits file is not going to fit in main memory. That's why we will be dividing it into the first stage as per the size of memory size. So this 5 gigabits file can be divided into 5 parts. So take the first part, which of 1 gigabit. Sort it and, again, write back to the disk. In that manner, we are going to take the next part. Each part of the relation will be sorted and the result will be written back to the disk. So here 5 files are generated. Or, we can call it firearms are generated or n is equal to 5 now in the next stage.
What we have to do is that, this again the main memory size is 1 gigabit, so if we bring all the blocks then it will fit and we are not able to write the output. So what we are doing is that from every run file that has been generated, we are going to read some part, so assume that here it is 150 megabits has been read from each file, so total data available is of 750, whereas 250 is blank or is available for writing the output. So consider this as an relation employee again, so select star from employee, ordered by name, this is our query, so how it will be executed? So let us assume that we can fit 3 buffers in main memory and 1 tuple for buffer. So, first stage is that divide the relation as many buffers it can fit in the main memory. So it can fit only 3 buffers and 1 buffer contains 1 tuple. That's why these 3 will be brought to the main memory, sorted, and again, result will be written back to the disk. And that's how. So, in last one, 2 are remaining. So, whichever is less than, we have to take into consideration and this will return back to the result. So, this is how the 4 runs has been created. Every run is sorted. Now, we have to merge it. So in the second stage, we have to read M-1 input buffers and 1 buffer for writing the output. So here M is 3, that SY, we will be reading only 2. So now we are having 4 runs, but all the 1 block of each run cannot fit. So we are going to take as many we can fit. So we are going to read only first 2, then next 2 and so on. And once it has been merged, we will go for the next 2 runs and next 2 runs and so on. So, here this first 2 will be taken. This is as we are assuming this is 1's buffer and finally 1 buffer is available for output. This will be compared and result will be written to the output buffer. Again this is complete. This will return back to the disk. So next will be taken. Again next will be compared and then result will be written to the output. Since first 2 runs are completed, we can go for next 2. Again next will be compared and then result will be written to the output. Since first 2 runs are completed, we can go for next 2. So, from 4, we have got to merge files. And these 2 will be compared. And then we will be getting the single sorted output.
Let B represent the number of blocks that contain records of relation R. In the first stage, we read every block of the relation and then write it out again. So the total cost here is 2 times B block transfers. Next, the initial number of runs is B divided by M. Since the number of runs shrinks by a factor of M-1 in every merge pass, the total number of merge passes needed is ceiling of log base M-1 of B/M. In each merge pass, we read every block once and write it once. There are 2 exceptions to this. First, in the final pass, we can produce the sorted output directly, without writing the result back to disk. Second, some runs might not get read or written in a pass. For example, if there are M runs available, we might merge only M-1 runs, and 1 run isn't accessed during that pass. If we ignore the relatively small savings from the previous effect, the total number of block transfers for externally sorting the relation is calculated as follows. It is B multiplied by open bracket 2 times the ceiling of log base M-1 of B divided by M plus 1 close bracket.